axioms prove two statements. One statement X and the other statement not X. In other words, the contradiction. So you get no contradictions. Because prior to that, especially due to a famous British mathematical logician named Bertrand Russell, he found certain paradoxes in the foundations of mathematics which plagued the philosophers, mathematicians thinking about the foundations of mathematics. So Hilbert came up with this idea of creating a formal system which by using no, he didn't actually do it, but he said, this is a research program, let's do this. So the Hilbert program, as it's called. So a bunch of axioms and rules of inference. You use rules to make conclusions based on the axioms. So the axioms and the rules of inference, making deductions. So this set of rules, axioms plus rules of inference together would allow you to prove consistently, with no contradiction, all mathematical statements. Well, and that was the big dream. And then along comes Gödel and just kills it. Can't be done. Impossible. And Gödel, well, I'll just say quickly, but what Gödel shows is that, given a formal system, powerful enough to do mathematics with the natural numbers, like there are formal systems that are less powerful, that are provably correct. In fact, Gödel himself showed, one of these famous formal systems was consistent and complete. I think he's got his PhD for doing that. But I'm getting now more into logic, mathematical logic. But anyway, Gödel says, so long as your formal system is powerful enough to make mathematical statements, for example, about the natural numbers, then you can find statements that are true, that are obviously true, but are not provably, you cannot prove that statement is consistent or inconsistent. I need to I need to study Gödel more formally myself. I'm just trying to get the actual details. So what Gödel proved was you have a set of axioms, and it's you can find statements that are obviously true, but you cannot prove that they're true or false from those axioms. So in other words, that set of axioms that you have is incomplete. Right? It's not enough, in other words, to prove or disprove the statement that you know for other reasons is obviously true. Okay? Now you may say, oh, all right, well, we'll add some more axioms so that we can prove that this statement that you're talking about is true or false. Okay? But that doesn't help, because then using Gödel's ideas, the incompleteness proof, okay, you now start with this new set of axioms, so the old set plus a few more, okay, and you can then prove that there's some other statement, some new statement, that you know is true for different reasons, but you cannot prove it true or false from that new set, well, augmented set of axioms. Okay, so you've always got this incompleteness, and it was just devastating to all those people who, like Hilbert, were hoping for a formal system that would make mathematics well-founded, have a strong basis. Destroyed it, absolutely shattered it, and people have been thinking for decades about the long-term implications of Gödel's famous results. And in a sense, Turing was fascinated by Gödel's work, and what Hilbert was trying to do, and at a very early age, early 20s, because Turing also brilliant, pretty well in attempting to answer some of Hilbert's questions, he took up the challenge of Hilbert's program, because it had various aspects, and out of that came the notion of the Turing machine. So some procedure, step-by-step procedure, with algorithms and so forth. So he invented the Turing machine, and out of that came the notion of the universal Turing machine that could do virtually anything. Hence, a programmable universal Turing machine. So you could program it to do almost anything. But he also showed that some things are just impossible to prove, to calculate. Especially his famous halting problem, the Turing halting problem, and we'll talk about that at length in this course. So he inspired a lot of people to go ahead and actually build real machines in an engineering sense that would be programmable and universal. You could use them to solve all kinds of different problems. So out of his work in logic and the foundations of mathematics came the computer industry. Right? So maybe I'll give a few extra lectures on that, because it's fascinating. So I haven't looked in detail at the content of this text on those sort of things. But if there are some interesting gaps, I might add a few lectures to fill in the details, because it's just so fascinating. Right. Well, after that longish diversion, let's now start thinking about how to go about proving this particular example. So here's your statement, right? Your theorem statement. And then you start. Then these lines here give you an idea on how to approach the problem, how to go about thinking of a possible proof. Right. So this is sort of an example of proof construction, if you like. Okay. So here's the statement here. These just 1.5 lines of the theorem statement. So for all, right, for any graph G, just G, big G, just the name symbol you give for any graph, the sum of sigma, the sum of the degrees of all the nodes in the graph is an even number. Now, can you remember the degrees of a node? Remember the definition for that? It's the number of edges that connect to the node, right? In other words, the number of lines that connect to that dot or little circle. Okay, that's the degree. So if you sum up the degrees of all the nodes, that number will be even. Okay, that's the theorem statement. And then you need to we'll start thinking about how would you prove that. So. Well, now I was saying a bit before, let's try for some concrete examples to see that it's true. Well, here's a fairly simple graph, right? Just 3 nodes, 3 edges, and so sum up all the degrees. Well, this one here, it has two edges that connect with it, so the degree of this one is 2. And this node here, similar story, two edges connect to it, so its degree is 2, and it's the same here. So total will be 2, 2, 2, so 6. Well, that's an even number. Okay, well, so far that's true. So now maybe try another example, say a little bit more complicated. Now in this case, the degree was the same for each node, and in this case, that's not true. For example, the degree of this one is 4, the degree of these two is 3, the degree of these two is 2. So now if I move from left to right, and count up the degrees of each one. So it'll be 2 plus 3 plus 4 plus 3 plus 2. Okay, and moving left to right. So 2 plus 3 plus 4 plus 3 plus 2. 5, 9, 12, 14. 14. Again, an even number. Right? Okay, so you're beginning, you can do this quite a lot. And every time you will get an even number. So you begin to be suspicious that maybe this theorem statement is actually true. Right? Maybe it's true in all cases. Strictly true. So, well, but maybe not. Maybe there are special cases where it's false, and you have to find one. Remember? Find a counterexample. So go, try and find a counterexample. Now, humorously, I've put here, don't hold your breath. That's an American expression, and it's used, I'm assuming the majority of you are not native English speakers. Don't hold your breath. You say that when you expect that the other person will not be able to do something that they're trying to do, because it's either very difficult or impossible. So when you tell the other person, don't hold your breath, is because if they do hold their breath while they're trying to finish this task that's virtually impossible, very, very difficult, they may die because they'll not have enough air. Right? So this expression is don't hold your breath. Now, the humor is because this theorem statement is actually true, and a session or two will actually prove it. Right? It's actually true. So if it's true, therefore there is not even one counterexample. There is no counterexample because it's true. Right? A theorem is true if it's true in all cases. In other words, there is no counterexample. There are no exceptions. Right? It's true in all cases, strictly. Right? So don't hold your breath, because you could keep trying for finding a counterexample, and you won't find one. I mean, you might try something like this. Like here's a node, and here's an edge, but it's not an edge because that is not a graph. No, because an edge has to be connected at both ends. So you'd have to have a node here. Okay. So saying, oh, well, look, that if that's a graph, the total number of degrees is just 1. Well, that's an odd number, but that's not allowed because that's not a graph. Okay. So you can rule out that possibility. Because a graph, each edge has to be connected to two nodes. By definition, that's what an edge is, right? It's the line between connecting two nodes, by definition. So that does not satisfy the definition of a graph. It's not a graph. Okay. How about this one? We're still looking for counterexample.